Close your eyes now and allow the rhythm of your breathing to settle into a gentle and natural flow. Inhale slowly, and as you exhale, feel the tensions of the day beginning to soften and release. With each breath, imagine yourself becoming lighter, as if you are gently detaching from the world of solid things. We are preparing for a journey not of the body, but of the mind, a voyage across the vast and quiet ocean of space. Picture the Earth not as a map, but as a pale blue dot suspended in the profound and silent blackness of the cosmos. From this vantage point, the familiar hustle of our daily lives recedes into a tranquil and distant whisper. The universe from here is a realm of majestic calm, of celestial motions measured in eons, not minutes. We are going to explore one of the most captivating mysteries this cosmic quiet holds, the story of the interstellar visitors. These ancient travelers from distant stars are the perfect subject for a wandering and contemplative mind. Their tale is one of almost unimaginable distances of time, spans that dwarf human history, and of profound solitude. There is no urgency here, only the slow and grand narrative of physics and chance written across the galaxy. So, let your awareness expand outward beyond the walls of your room, beyond the atmosphere and into the void. We leave behind the bright and noisy world and turn our attention to the dark and silent spaces between the stars. In this darkness we will find motion, we will find history, and we will find a deep and resonant peace. Listen to the words and let them paint images in the darkness behind your eyelids, images of ice and rock sailing through the eternal night. There is no need to grasp for every fact or remember every detail, for this is a story to be felt as much as it is to be understood. The goal is not to stay alert, but to let the grandeur of the cosmos lull your conscious mind into a state of wonder and rest. The universe has been here for 13 billion years, and its stories can wait for you to drift into sleep. Tonight we begin with the simplest of actions, an action as old as humanity itself. We look up. We look up not with telescopes, but with our imagination, and we ask a simple and powerful question: are we alone in this great expanse? The answer, as we are beginning to learn, is that we are not alone in the way we once thought. Our solar system is not a perfectly isolated island, but a participant in a gentle and continuous exchange of material with the galaxy. The first chapter of this realization began not with a bang, but with a faint and fast-moving speck of light in a telescope's eyepiece. But before we meet that first confirmed traveler, we must understand the context of its arrival. We must comprehend the architecture of our own solar home, the very walls that these visitors have breached. So let us begin our journey at the very edge in the deep freeze of our system's frontier, a place of sleeping giants and primordial relics. Imagine the sun as a distant and shrunken star, its light a feeble glow, its warmth a forgotten memory. Here in this perpetual twilight lies the Kuiper Belt, a vast disk of icy worlds and frozen debris. It is a realm of silence and stillness, where Pluto and its kin trace their slow and cold orbits. But this is only the inner courtyard of our solar system's domain, a mere introduction to the true frontier. Stretching far beyond to a distance of nearly a light year lies a colossal and spherical cloud of icy planetesimies. This is the Oort cloud, the solar system's final outpost, a gravitational reservoir of 1 trillion icy bodies. These objects are so distant and so loosely bound to the sun that they are essentially sleeping in the interstellar deep. The passing gravity of a nearby star, the gentle tug of the Milky Way's galactic tide, any small nudge can dislodge them. Some are nudged inward, falling for thousands of years, to become the long-period comets that grace our inner solar system. Others are nudged outward, cast adrift completely, to begin an eternal journey between the stars. This is the key. The Oort cloud is not a perfect shield, it is a dynamic and leaky border. For every object that falls inward from its depths, there must be objects from other stars falling in from the outside. The solar system we now know is porous. It is a celestial castle whose walls are permeable to the dust and pebbles of the galaxy. This understanding transformed our view of cosmic solitude. The gates were opening. We only needed to learn how to see the travelers passing through. The stage was set. Our understanding of the solar system's boundaries had been redefined and our technology was advancing. All we needed was for a messenger to arrive, and in October 2017 that messenger came. It was detected by the Pan-STARRS telescope in Hawaii, a relentless mechanical eye scanning the heavens for moving objects. At first it was just another dot among millions catalogued as 1I. 2017 won a giant technical designation. But its orbit was immediately unshockingly different from anything ever seen before. It was not a closed ellipse, the path of a body bound to our sun. It was an open hyperbola. It was moving too fast, far too fast to be a permanent member of our solar system. This was not an object from our Earth cloud being perturbed inward. This was an object from interstellar space making a single and fleeting pass. The discovery sent a wave of excitement through the global astronomical community. The first interstellar visitor had been found. It was given a name, MUA, a Hawaiian word meaning a messenger from afar arriving first. The data began to trickle in, and with each new observation the mystery only deepened. MUA was small, perhaps only 100 meters long, and its light curve revealed an extraordinary shape. It was tumbling, and the dramatic changes in its brightness suggested it was highly elongated, perhaps 10 times as long as it was wide. A cosmic cigar tumbling through the void after its unimaginably long journey. It showed no signs of outgassing, no visible coma or tail of gas and dust that would mark it as a typical comet. Yet precise tracking of its path revealed a tiny and ungravitational acceleration. It was not following a path dictated by gravity alone. Something was giving it a minuscule push, and for a time every explanation seemed fraught with mystery. Was it venting gas from hidden pockets, the subtle thrust of a dying comet? Or was it something else, something so exotic it sparked wild and ultimately unsupported speculation about artificial origins? The scientific process, however, is one of patient analysis, and Occam's razor, the simplest explanation, is usually the correct one. Further study suggested that MUA was likely a planetcement, a building block of a planetary system ejected long ago. Its strange acceleration was most likely caused by the sublimation of hydrogen ice, a process that would not produce a visible coma. It was a new type of object, a shard of a world that never was, from a star we may never identify. It was a messenger indeed, but its message was one of cosmic violence and the dynamic chaos of young solar systems. It told us that the processes that formed our own system, the gravitational scattering and clearing of debris, are universal. It told us that the galaxy is likely filled with such drifting relics, the archaeological remains of planetary birth, and as quickly as it arrived, it was gone, speeding back out into the interstellar, while cleaving a trail of questions in its wake. But to MUA was just the beginning, the proof of concept that interstellar objects were real and within our power to detect. The universe, it seemed, was eager to send us another and clearer message, and just 2 years later it arrived. In August 2019, an amateur astronomer in Crimea, Gennady Borisov, spotted a faint and fuzzy object with his homemade telescope. Its orbit, like MUA's, was a perfect hyperbola, another undeniable visitor from beyond. This one, however, was unmistakably a comet. It was active, displaying a bright coma and a distinct tail. Designated to I Borisov, it was a familiar sight in an unfamiliar context, a cosmic snowball from another star. Here was the diversity we had been waiting for. MUA the strange and rocky, or metallic asteroid, and Borisov the classic comet. Their contrasting natures confirm that the population of interstellar objects is as varied as the population of our own solar system. The galaxy is not just tossing random rocks our way, it is sending a representative sample of its planetary building materials. Studying them is like collecting bottles washed up on a shore. Each one contains a message from a distant land. The discovery of these visitors marks a new epoch in astronomy, the beginning of interstellar archaeology. We are no longer limited to studying our own solar system. We can now hold pieces of others in our virtual hands through our telescopes. It opens a window into the chemical and physical conditions around other stars, conditions that may be common or may be unique. It allows us to test our models of planet formation on a galactic scale, to see if our solar system is typical or an outlier. And perhaps most profoundly, it raises the tantalizing possibility that the seeds of life itself could be hitchhiking on these cosmic rafts. This is the story we will unfold in the quiet of this night, a story of mystery and of our expanding place in the cosmos. But for now, let the simple fact of their existence settle in your mind. We are connected to the galaxy by a slow and silent river of ice and stone. There is a profound comfort in this connection, a sense that we are part of a much larger and dynamic system. So, as we delve deeper into the science of these wanderers, carry this feeling of connected solitude with you. Let the vast timelines and immense distances soothe your thoughts, for in the cosmic scale all worries are small and transient. The universe is going about its business, and we are here safe and warm, privileged to be its observers. Now let us turn our attention to the nature of these messengers themselves, to understand what they are made of and the stories they carry within their frozen hearts. Let your mind now drift from the vast and empty highways between stars to the travelers themselves. What are these solitary voyagers made of, and what can their primordial substance tell us about their origins? The key to understanding these messengers lies in the fundamental building blocks of planetary systems. In the swirling protoplanetary disk of gas and dust that surrounds a young star, particles begin to collide and stick. Dust grains become pebbles, pebbles become planetesimments, the rocky and dicey embryos of future planets. This is a violent and chaotic process, a gravitational scrum where only the largest bodies secure stable orbits. Countless planetesimments are shattered, consumed, or flung away into the darkness by the gravitational influence of giant planets. It is from this chaotic ejection process that our interstellar visitors are born. They are the refugees of cosmic construction. They do not begin their journeys as sleek and streamlined objects, but as fragments, undroppable piles of a disrupted past. Their shapes, like that of UA, are often irregular, sculpted by ancient impacts and the relentless pull of tidal forces. To comprehend their nature, we must first classify them. Nature has provided two broad categories. The first is the interstellar comet, like Borisov, a body rich in volatile ices that awaken when warmed by a star. The second is the interstellar asteroid, like UA, a seemingly more rocky or metallic body devoid of obvious activity. Let us first descend into the frozen heart of a comet, the most ancient and well-preserved relic of a solar system's youth. The classic model is the dirty snowball, a mixture of water, ice and frozen gases and darkened organic rich dust. But this model has evolved. We now understand them more as snowy dirt balls with a higher proportion of dust and rock. Imagine a fragile and porous aggregate of ice and dust and complex carbon-based molecules, all loosely bound by gravity. This structure is key to their behavior as they approach the Sun. The ices do not melt, they sublimate. They transform directly from solid to gas, jetting off the surface and carrying dust particles with them. This is the birth of the coma, the vast and tenuous atmosphere that can swell to be larger than planets. The solar radiation and wind then push this gas and dust away, forming the iconic tails that can stretch for millions of miles. The gas tail, glowing with ionized molecules, always points directly away from the Sun, a cosmic windsock. The dust tail, reflecting sunlight, curves gently along the comet's orbital path, a trail of glittering debris. To I. Borisov was a textbook example of this process, a visitor that felt the Sun's warmth and responded in a familiar way. Spectroscopy analysis of its light revealed the chemical fingerprints of cyanogen, gas and diatomic carbon. These are common constituents of comets within our solar system, a powerful indication that the chemistry of planet formation is universal. The very ices and organics that graced our inner solar system 4 billion years ago are the same as those around other stars. But within this familiarity lies a deeper mystery: the specific isotopic ratios of these elements. Isotopes are different forms of the same element, having the same number of protons, but different numbers of neutrons. The ratio of deuterium to hydrogen in a comet's water ice, for instance, is a sensitive probe of its formation conditions. It depends on the temperature and radiation environment in the specific region of the protoplanetary disk where the ice formed. By measuring these ratios in an interstellar comet, we can effectively read the birth certificate of another solar system. We can ask, was the disk around your parent star hotter or colder than ours? Was its chemistry more or less complex? Borisov offered us this chance, and the results were both astonishing and deeply significant. The deuterium to hydrogen ratio in Borisov's water was found to be exceptionally high, higher than almost any comet measured in our system. This single measurement tells a story. It suggests that Borisov formed in the cold and outer reaches of its planetary system. Perhaps it was forged in a region rich with organic material, where cosmic rays had billions of years to bombard the ice. Or perhaps it formed around a different type of star altogether, a cooler red dwarf or a more massive and hotter star. This is the profound power of these visitors. They are not just rocks, they are encoded libraries of galactic diversity. Now let us turn to the other and more enigmatic class, the interstellar asteroids, the dark and silent wanderers. Oumuamua was our first and only example, and its lack of obvious activity marked it as fundamentally different. Without a coma of gas and dust, astronomers had to determine its composition solely from the sunlight it reflected. Its reddish color suggested a surface that had been irradiated from millions of years of cosmic tan from interstellar space. This surface could be rich in complex organic compounds called tholins, created when simple ices are bombarded by radiation. Or it could be the signature of a metallic surface weathered by the same relentless cosmic rays. The most puzzling aspect was its shape. Extreme elongation is uncommon among solar system asteroids. It suggests a unique formation history, perhaps as a shard from a catastrophic collision between larger bodies. Some theories propose it could be a fragment of a planet that was torn apart by its dying star. Others suggest it might be composed of exotic ices, like molecular hydrogen that could sublimate without leaving a visible trail. This would explain its non-gravitational acceleration, the gentle push that altered its course. If it were made of nitrogen ice like the surface of Pluto, its sublimation would be invisible to our telescopes. It would have been a chip off a Pluto-like world from another star, a breathtaking concept. The truth is, with only one such object, we are left with a magnificent puzzle, a single data point begging for context. The population of interstellar space is likely a continuous spectrum from pure icy comets to pure rocky asteroids. Most may be somewhere in between dormant comets with sealed surfaces or rocky bodies with pockets of exotic ice. Their diversity is a direct reflection of the infinite variety of environments in which they formed. To trace them back to their source, we employ the powerful tools of celestial mechanics and galactic astronomy. When an object like Oumuamua is detected, astronomers immediately calculate its hyperbolic trajectory backwards in time. They trace its path through the gravitational fields of the Sun and planets back to the point where it entered our system. This gives us its incoming velocity and direction, its vector of approach from the galactic community. We then compare this vector to the motions of nearby stars searching for a past encounter. Stars are not fixed, they orbit the center of the galaxy, each with its own proper motion through space. By running the galactic clock backwards, we can see if our visitor passed close to any star system in the last few million years. For Oumuamua, no convincing stellar parent was identified. Its journey is simply too long. It had likely been traveling for hundreds of millions, perhaps even billions of years, a relic from a forgotten time. During its epic voyage, it would have passed through countless star fields, its path gently perturbed by stellar gravities. It is a true citizen of the galaxy, belonging to no single star, but to the Milky Way itself. Borisov, on the other hand, showed a possible origin from the direction of a binary red dwarf system. But even this is uncertain. The probabilities, although the galaxy is a vast and dynamic place. This difficulty in pinning down their homes is not a failure, but a testament to the scale of the galaxy and the age of these objects. They are the enduring nomads of the cosmos, their point of origin erased by the sheer passage of time. They carry the averaged signature of the galactic disk, having been mixed and stirred by countless stellar encounters. Their very existence and numbers allow us to estimate how much material is drifting between the stars. Current estimates suggest that within the orbit of Neptune alone there may be thousands of such interstellar interlopers. They are constantly passing through our system, most too faint and fast for our current telescopes to detect. Each one is a unique specimen, a core sample from a distant world we will never see directly. They are the universe's way of sharing its secrets, sending us physical samples across the light years. As you lie in the quiet darkness, consider the sheer statistical reality of this. At this very moment, one of these ancient wanderers. It is silently and invisibly passing through the plane of the solar system, a ghost from a distant sun. It asks for nothing, it demands nothing. It is simply a piece of cosmic data, a story waiting to be read. And with that thought, let us now explore how we might one day reach out and touch these stories, how we might send our own messengers to greet them. The detection of interstellar objects from our telescopes on Earth is a monumental achievement. But for the true planetary scientist, it is only the first and most passive step in the process of discovery. To truly read the stories locked within these cosmic messengers, we must get closer, much closer. We must send robotic emissaries to rendezvous with these visitors, to photograph them and to analyze their composition directly. This ambition, however, collides with one of the most formidable challenges in modern space exploration. The challenge of speed and of time. These objects are not waiting for us. They are passing through at incredible velocities. Oumuamua, for instance, was moving at nearly 60 kilometers per second when it was discovered, already on its way out. By the time we had confirmed its nature, it was already too far away, unmoving, too fast to even consider a chase. This is the fundamental problem. We are like shoreline observers trying to launch a boat to intercept a ship that has already passed. The key to solving this lies not in faster rockets, though they will help, but in preparation and prediction. We must have missions designed and ready to launch on extremely short notice when the next ideal candidate is found. This requires a new paradigm in space mission design, one built around rapid response and flexibility. The European Space Agency is pioneering this approach with a remarkable mission concept called the Comet Interceptor. Scheduled for launch in 2029, this mission is fundamentally different from all Comet missions that have come before. Instead of traveling to a known comet, it will launch first and then wait. It will journey to the Sun-Earth Lagrange point, to a gravitationally stable parking spot 1,000,000 miles from Earth. And there it will wait patiently like a cosmic sentinel for up to 3 years for a suitable target to be discovered. The ideal target would be a pristine comet from the outer solar system, or even better, a second interstellar object. When such an object is found, the Comet Interceptor will fire its engines and embark on a high-speed intercept course. It will be a fast and fleeting encounter, a high-velocity flyby measured in hours or minutes, not months. But in that brief window, its suite of instruments will capture images, map the surface, and analyze the composition of the visitor. It will be our first dedicated attempt to conduct a close-range survey of an object from another star system. This mission represents a profound shift in strategy, from chasing specific targets to creating a standing capability. It acknowledges that the most interesting discoveries in the coming years may be those we have not yet made. NASA and other space agencies are studying even more ambitious concepts for the future. Some involve designing spacecraft with advanced propulsion systems, like solar sails or ion drives that can achieve higher speed. Others envision spacecraft that could not just fly by but actually match velocity with an interstellar object. A rendezvous mission would be exponentially more difficult, but the scientific return would be revolutionary. Imagine a spacecraft drifting alongside a primordial shard from another world for months, or even years. It could map its entire surface in exquisite detail, drill into its interior, and analyze its chemical makeup molecule by molecule. It could look for amino acids and other complex organic molecules, the building blocks of life. It could measure the ratios of different isotopes with precision far greater than any Earth-based telescope. The data returned would be the equivalent of receiving a carefully curated sample from a distant planetary system. But how do we power such a mission across the vast and dark reaches it would need to travel? The answer may lie not in conventional chemical rockets, but in harnessing the physics of the solar system itself. Gravity assists, a technique perfected over decades, could be used to slingshot a spacecraft onto a high-speed trajectory. By flying close to planets like Jupiter, or even the Sun itself, a spacecraft can steal a tiny fraction of their orbital energy. This can accelerate a probe to velocities that would be impossible to achieve with rockets alone. Another possibility is to use the Sun itself as a gravitational lens, a concept that borders on science fiction. Einstein's theory of general relativity tells us that massive objects like the Sun bend space-time and thus bend light. This means the Sun can act as a gigantic lens, focusing light from distant objects at a specific point in space. A spacecraft positioned at this focus point hundreds of times further from the Sun than Earth could achieve incredible magnification. It could in theory take detailed images of an interstellar object's surface from a great distance, resolving features just meters across. The engineering challenges are immense, but the principles are sound and rooted in fundamental physics. There is also the exciting possibility of intercepting an object that is not just passing through but is temporarily captured. The same gravitational dynamics that sometimes capture comets from our own Oort cloud could theoretically capture an interstellar object. A visitor from another star could be nudicated into a loose orbit around the Sun, becoming a temporary moon. This would give us years or even decades to study it, a golden opportunity for repeated observations and even multiple missions. The search for such captured interstellar objects is already underway, sifting through data on known asteroids and comets. Finding one would be like discovering a free sample from another star system delivered to our cosmic doorstep. As these missions transition from concept to reality, they force us to confront deeper questions. What protocols do we follow if we discover complex chemistry on an interstellar object? How do we handle the potential, however remote, of discovering signs of biological activity? International space law is already grappling with these questions, developing frameworks for the ethical exploration of these objects. The Outer Space Treaty, the foundational document of space law, prohibits the harmful contamination of celestial bodies. This applies equally to an asteroid from our belt and to a comet from another star. We have a responsibility to explore these visitors with care, to preserve their scientific integrity and to protect our own planet. The pursuit of these missions is not just about satisfying scientific curiosity, as profound as that is. It is about fundamentally expanding our reach and our understanding of our place in the cosmic community. By reaching out and touching a piece of another planetary system, we become more than observers of the galaxy. We become active participants in its exploration. We become interstellar archaeologists. The quiet and patient work of mission planners and engineers is laying the groundwork for this next great leap. Their calculations and designs are the blueprints for our first tangible contact with other solar systems. So, as you drift towards sleep, imagine a silent spacecraft waiting at its celestial gate. It is powered down and dormant, its sensors quiet, its engines cold. It is waiting for a call from Earth, a call that will tell it a new island has been spotted in the cosmic ocean, and that it is time to set sail. Let your mind now wander to the deepest implication of these interstellar wanderers, an idea both ancient and revolutionary. What if these messengers do not just carry the secrets of rock and ice, but the very seeds of life itself? This concept is known as pansperium, the hypothesis that life exists throughout the universe and can be transported between planets. It is not a new idea. The Greek philosopher Anaxagoras proposed something similar in the 5th century BC. But for the first time in human history, we have tangible evidence of a plausible mechanism for its occurrence. Interstellar objects like Oumuamua and Borisov are the ideal vessels for this cosmic transplantation. They are the driftwood carried on the galactic currents between the islands of habitable worlds. Consider the journey of such a life-bearing object, a concept we might call lithopansperium if the life is hidden within rock. A massive impact on a living world like early Mars or a distant exoplanet that could eject fragments of crust into space. Some of these fragments could contain microorganisms trapped in a state of suspended animation. They would be encased in a protective shell of rock, shielding them from the deadly radiation of interstellar space. For millions of years, this rocky ark would drift through the cold and silent void, its microbial passengers frozen in time. Eventually, by the sheer statistics of galactic motion, it might approach another star system. The gentle gravity of a planet that could pull it in, guiding it through the atmosphere in a fiery descent. The heat of entry would sterilize the outside, but the interior could remain cool, protecting its precious cargo. Upon impact, the microorganisms finding themselves on a new and fertile world could potentially reanimate. It is a dramatic and seemingly fantastical scenario, yet every step of this process is within the realm of physical possibility. We know that impacts can eject material from planets. We have found Martian meteorites here on Earth. We know that certain microorganisms known as extremophiles can survive the vacuum and radiation of space. Tardigrades, for instance, those microscopic water bears, have been shown to survive exposure to the space environment. We know that rocks can protect their interior from the heat of atmospheric entry, as proven by every meteorite we recover. The individual steps of lithopansperium are therefore not science fiction, they are documented scientific facts. The great unknown is whether the entire sequence could be completed over an interstellar distance. Could life remain viable after millions of years of cosmic radiation exposure? Could it survive the final violent impact on a new world? The answers are not yet known, but the discovery of interstellar objects makes the question suddenly urgent and empirical. If life can indeed hop between stars, then the tree of life in the galaxy might not be a collection of isolated saplings. It could be a vast and interconnected forest with genetic material being exchanged across mind-boggling distances. Life on Earth then might not be a unique miracle but a local branch of a galactic biosphere. Our origins could literally be written in the stars, not just in the metaphorical sense of being made of stardust, but in the literal sense that the spark that began biology on our planet arrived on a rock from another world. This does not solve the problem of how life began, it merely pushes it back a step to another time and place. But it profoundly changes our understanding of life's tenacity and its potential distribution in the cosmos. Life would not be a fragile flame flickering in isolation on a few lucky planets. It would be a cosmic infection, a resilient and persistent phenomenon that can spread across star systems. The implications for the future of humanity are equally staggering. If we ever establish permanent settlements on other worlds, we might inadvertently contaminate them with Earth life. Or we might discover that life is already there and that it shares a common ancestry with us, a cousin from across the galaxy. The discovery of a single microbe on an interstellar object with DNA or RNA similar to ours would be the most profound discovery in history. It would tell us that we are not alone in the universe and that we are all part of the same biological family. This idea of cosmic connections brings a new dimension to the quiet solitude of the interstellar night. The emptiness between stars is not just a void, it is a highway for the most precious cargo in the universe, the code of life itself. The vast temescals that once seemed to separate us from other worlds become the very medium that connects us. A journey of 1,000,000 years is nothing to a bacterium frozen in a rock. It is simply a long night's sleep. As you lie in your bed in the darkness of night, consider this possibility. The ancestors of the life that surrounds us, the trees, the birds, the microbes, and even ourselves, might have begun their journey to Earth not in a warm pond on our planet, but on a world orbiting a star now dead. They traveled for eons asleep in the heart of a wandering stone until our young planet crossed its path. We are all the children of the galaxy, our heritage written not in history books, but in our very cells. This is not a call to abandon the search for how life began on its own terms. That search remains vital. It is an invitation to expand our imagination, to consider that our story might be grander and more interconnected than we ever dreamed. The silent and dark space that induces sleep is the same medium that cradles and transports the potential for life. There is a deep and abiding poetry in this, a harmony between the emptiness and the fullness of creation. So as you feel sleep approaching, let this thought be your lullaby. You are not just a citizen of Earth, you are a citizen of the Milky Way. Your existence is part of a story, that spans light years and millennia, a story of cosmic driftwood taking root. And in that vast and timeless narrative, your rest tonight is but a single peaceful breath. And so we return from our journey to the edge of the solar system and beyond. We have followed the path of the interstellar messengers from their violent birth to their silent voyage. We have contemplated their icy hearts and rocky shells and the profound secrets they may carry within. We have envisioned the spacecraft that might one day reach out and touch these ancient wanderers. And we have considered the staggering possibility that they might be the carriers of life itself. Now it is time to let these grand ideas settle in the quieting landscape of your mind. There is no more need for analysis, no more need for concentration. The facts and the theories have done their work expanding your perspective and calming your spirit. Feel the weight of your body against the bed, a tiny planet in its own right, held by gravity's gentle embrace. Listen to the rhythm of your breath, a slow and steady tide in the ocean of your body. The same elements that cycle through you, the carbon, the hydrogen, the oxygen, were forged in the hearts of long-dead stars. You are, in the most literal sense, a child of the cosmos, momentarily awakened, aware of its own existence. The interstellar visitors we discussed are your distant relatives, also made of stardust on a different path. Their journey is measured in billions of years, yours in decades, but you share a common origin in the Big Bang. This connections, this unity with the universe, is the ultimate source of peace. The anxieties of the day, the worries about the future, they are all so small against this cosmic backdrop. You are safe, you are home, you are part of an immense and beautiful whole. Let the image of the pale blue dot return to your mind's eye. See it suspended in a sunbeam, a tiny and fragile world of water and cloud. From here no borders are visible, no conflicts are apparent, only a quiet world of stunning beauty. This is your home, and from this perspective its peace is absolute. Now let that peace flow into you, filling you with a sense of deep and quiet belonging. The universe is not a cold and empty place. It is a place of wonder and mystery and connection. And as you sleep tonight, your dreams may wander through the star fields. You may dream of silent comets with glittering tails, or of strange and elongated asteroids tumbling through the void. Or you may simply dream of nothing at all, wrapped in the deep and comforting silence of space. Allow your breathing to become even slower and deeper. With each exhale, release any final remnants of tension in your body and mind. You have journeyed far tonight across space and time. Now it is time to rest, to recharge, to return to the silent source from which all things come. The universe is ancient and patient. It has all the time in the world for you to sleep. So let go fully and completely. Allow yourself to drift weightless like an interstellar traveler on the currents of the galaxy. You are safe. You are secure. You are home. Good night.